Good day, and welcome to CFE Media's Virtual Training Week. For this session on enabling predictive maintenance using condition monitoring, we'll be joined by Brad Hopkins, Director of Condition Monitoring and of Product Management in IoT Services at HID Global. I'm Kevin Parker, an editor with CFE Media and Technology. Following the presentation, be sure and stay tuned for the live Q&A. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. Certificate of completion will be issued to each participant. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. Getting to a true predictive maintenance strategy for your plant requires planning and having the right tools. In this session, we will review a variety of maintenance strategies, including run to failure, preventive maintenance, and predictive maintenance. Improve your understanding of decision-making in a manufacturing environment by attending this session. You'll learn how the use of condition monitoring technology enables predictive maintenance, how condition monitoring is best used to supplement and not replace decision-making, and we will explore the basics and advanced levels of maintenance strategies. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left-hand side of the screen below the session's agenda. If you would like to take notes within the session, click on the left panel labeled Notes to do so. This session is available on demand if you need to come back at any time. Please remember that this session will be made live at 10 a.m. Central, 11 a.m. Eastern, followed by a question and answer session. You can see the Q&A details in the Meetings tab on the left-hand side of the screen. The exam will be posted on CFE Media websites with the on-demand version of this webcast. The exam is for one RECEP Basic Certified Professional Development Hour. Before turning to our presentation, we'd like to share a brief video from today's sponsor.
You already know that real-time predictive maintenance is the best way to monitor the health of industrial equipment and prevent unplanned downtime, but that can be expensive. Did you know that with HID condition monitoring, you can afford to monitor all essential systems in the manufacturing process? Don't stop at just expensive equipment. Protect your entire workflow with HID beacons on every machine, all with easy deployment, real-time analytics, and machine learning. See how your business can avoid costly failures with HID condition monitoring. Because isn't every asset in your business mission critical?
Welcome back. I'd now like to introduce today's speaker. Brad Hopkins is the Director of Condition Monitoring and of Product Management in IoT Services at HID Global. Brad's background is in dynamic systems, signal processing, data science, machine learning, and vibration-based condition monitoring. His bachelor's, master's, and doctorate in mechanical engineering from Virginia Tech were awarded in 2008, 2009, and 2012, respectively. During this time, he conducted research in the area of dynamics and control systems. Previous positions include condition monitoring project engineer and senior data scientist at Amstead Rail Company, as well as being with the adjunct faculty in the mechanical engineering department at Southern Illinois University. Brad, welcome to today's virtual training week session, and please go ahead.
Thank you, Kevin. Like Kevin said, my name is Brad Hopkins, and today I'm going to be talking about enabling predictive maintenance using condition monitoring. Before I jump into this, I'll give you a quick intro into the company that I work for and what we do. So I work for HID Global, which is a part of ASSA ABLOY. ASSA ABLOY is a global leader in access solutions, and at HID, we are a globally recognized company in providing access control, credentials, cards, etc. Within HID, we have a business area called Identification Technologies, and further a business unit called IoT Services. And we specialize in wireless technology for industrial, healthcare, etc. So this session is going to be about enabling predictive maintenance using condition monitoring, and it's part of a 3-part series. Following this, we will be doing a deeper dive into the fundamentals of vibration-based condition monitoring. And then in a 3rd session, I'll do a more practical discussion of using wireless sensors, looking at real-time data, and tying it all together with some real data and use cases for improving maintenance practices with condition monitoring. So let's start by looking at running a factory and how we would actually measure success. So a common KPI in running a factory is overall equipment effectiveness, or OEE. So OEE can be calculated using a simple equation, and the equation has 3 parts. The first part is what we would call availability. So we're looking at a specific piece of machinery or a specific work center, and we want to know that it's available to be used when we want to use it. So we would call that uptime or availability. Then we also want to look at performance. So we have some sort of expectation as to how quickly the machine or the workstation or the work center is going to be able to produce what we want it to produce. So when we're talking about performance, we're looking at speed as a percentage of our desired speed, or the time to produce 1 unit. And then finally, we want to look at quality as well. So we could call this first pass yield, where we're basically looking at the good units that are produced as a percentage of the total units started. So did we have to scrap any for various reasons? Did they all pass the quality check, etc.? So we can also expand this a little bit more and look at total effective equipment performance, which is basically just taking our OEE and also adding another variable called loading. And this is where we just want to know that the calendar time that we've actually scheduled for operation is truly available. So we can add that to the equation as well. But what we want to do, of course, is increase OEE or TEP. And in order to do this, we need to increase availability, increase performance, and increase quality. So if we want to increase these factors, then in practice, if we're running a factory and we want to do things efficiently, make good inspections, operations, decisions, etc., then we need to look at factors that could potentially reduce availability, performance, or quality. So when we're looking at availability could be decreased from planned downtime. So this would be an instance where we intentionally scheduled some downtime. Maybe we're not running 3 shifts, maybe we're not running on the weekend, so this is planned downtime. But that still, of course, does affect availability, but that can be part of our schedule plan. Something that's not part of the schedule plan, of course, is breakdowns, or what we would call unplanned downtime. So these are unexpected failures, unexpected downtime. When we're looking at performance, like I said, we're talking about speed. So if we have any sort of minor stops or anything that's going to slow us down, that's going to adversely affect performance. So any sort of speed loss, we want to decrease that to improve performance. And then quality, if we do have production rejects or rejects on startup, obviously we want to decrease those to improve quality. So there are many different factors that are going to play into running an operation well, running a factory well, but specifically we can target one of these that we traditionally in various scenarios have very little control over, which is breakdowns or unplanned downtime. So when we're talking about breakdowns or unplanned downtime, we actually get into quite a comprehensive and complex set of costs that we can incur whenever a breakdown actually happens. So it could be idle labor or overtime labor. It could be that we have to actually scrap the work in progress, that maybe if a part or a component isn't completed in a certain amount of time and a machine shuts down, then we actually have to scrap that and get rid of it. And then there, of course, are repair costs. If the breakdown caused a mess, there could be cleanup costs. Also, with certain operations that have to operate under certain guidelines and regional restrictions, there could be environmental or safety penalties that go along with that. And then, of course, restart costs. There's, for operations that are running maybe around the clock, 3 shifts, unplanned downtime leads to lost production, lost revenue. And then also, not to mention, just additional, intangible factors as well. So like delayed fulfillment could affect a company's reputation if you're not able to deliver product on time. When we're looking at the cost of unplanned downtime, they can vary drastically from operation to operation and vertical to vertical. So I'm showing some average industry cost. However, within each of these industries or each of these verticals, the actual cost of unplanned downtime for each operation can vary drastically. So on the order of hundreds to thousands to maybe hundreds of thousands of dollars an hour for the cost of unplanned downtime. So getting an understanding of what the true costs of unplanned downtime are really help to make a good decision on getting into some of what we're going to be talking about shortly, which is condition monitoring. So as you may know, in the world, there are hundreds of millions of motors running plants, consuming lots of electricity, producing lots of things. In general, we can break these down into 3 categories. So for larger motors, we would typically call these critical pieces of machinery, which usually comprise about 5 to 10% of the population or the fleet in an operation. And then slightly smaller motors, maybe running from 150 to 300 horsepower, are going to comprise a slightly larger percentage of the fleet or the population of motors in an operation. And historically, these motors are the ones that are going to be getting the most attention because they are expensive. If they break down, the repair cost, the replacement cost, the production cost, et cetera, can be quite high if these break down. However, if we look at the remaining balance, much smaller motors, this in fact comprises the majority of the population in a factory. So if we just look at, for example, some different motor sizes and what they might actually cost to purchase, balance of plant motors typically could be hundreds or maybe low thousands of dollars. But when you're looking at larger pieces of machinery that are in the tens of thousands of dollars, or expensive turbo machinery that could be hundreds of thousands or even millions of dollars, those actual equipment costs can get quite high. We do have this interesting scenario, though, where the majority of the motors that are in a factory are balance of plant motors, and they are oftentimes the most expensive to maintain per horsepower, simply because they don't leverage that economy of scale that a larger motor is going to get, where you have so many small motors, looking after all of them takes a lot of time. So frequently we're going to see these smaller motors getting the least amount of attention in terms of maintenance and inspections, et cetera. So to perform maintenance on a fleet, we can take many different strategies, and depending on the organization, these could be broken up into many different levels or various granularities. But to keep things simple for the purpose of this discussion, I'm just going to cover 3 main levels of maintenance. So the most basic maintenance strategy is what we would call run to failure. And this is basically letting a machine run until it breaks down. So there really is no maintenance involved at all in this. So think of this like a light bulb where you screw it in and then you leave it for several years, and when it goes off, you just go in and replace it. And this is very common in practice. You could have small balance of plant motors that are running a conveyor belt, and an operation will just allow that motor to go until it burns out. And when it burns out, the maintenance manager will go in and replace it very quickly. So depending on the operation, it may or may not be a suitable way to address the operation itself or the maintenance. However, if this is used in a scenario where it's potentially damaging, you could have catastrophic failures, you could have safety risk, and then of course, that risk of unplanned downtime that we just talked about. The next level up of maintenance strategy is what we call scheduled maintenance or preventive maintenance. And this is when you will schedule maintenance at regular intervals, and that time interval is selected so that you're going to reduce the number of machine failures. So this typically requires some sort of historical performance data of a class of machines and then scheduling a maintenance interval accordingly. So you can think of this as maybe like getting the oil changed in your car, where you get it changed every 5,000 miles or 10,000 miles or 15,000, depending on the quality of the oil that you get. Or maybe you get it changed every 3 months, 6 months, every year. Either way, there is a schedule as to when you're getting that changed. The highest level of maintenance, though, is what we call condition-based maintenance or predictive maintenance. And this is when we are actively monitoring the health state or some sort of state of the asset, doing condition monitoring on it, and then performing maintenance in response to the known health of that asset or a predicted health of that asset. So the obvious advantage is that if we can implement condition-based maintenance or predictive maintenance, we're going to have a substantial reduction in maintenance and inspection costs. We can have a substantial reduction in unplanned downtime. However, this is oftentimes expensive. It's not always expensive, but it can be. So we do run into the challenge of finding the ROI for a condition-based maintenance strategy, which we'll talk about a little bit more later. So like I said, to do predictive maintenance or condition-based maintenance, we need to implement a condition monitoring solution. So I'm going to walk through, once again, 3 levels now with condition monitoring solutions and see how these play out and what advantages and disadvantages they have. So the most basic level of condition monitoring is what we would call fault detection. And that is just simply determining that something happened. So we don't necessarily know what happened or when something will happen in the future, but we know that something happened. A state has changed, temperature has changed, vibration has changed, and we think that this might be related to a fault in the system. So this is typically the lowest cost condition monitoring solution to implement, and typically the simplest. Of course, the downside, though, is when you're using fault detection, the output is oftentimes very binary. You're saying there is a fault or there isn't a fault. And as you may know, whenever you're using that type of approach, you subject yourself to the risk of false positives or false negatives. So a false positive is when we say that something is a fault when it actually is not. And a false negative is when we miss something. So when we say that the system is healthy and it is in fact not healthy. So the obvious risk of having a high false positive rate is if we're constantly saying that something is faulty when it's not, then we're actually increasing our inspections costs because we're going to look at something when we don't actually need to. Obviously, if we're missing it, then the condition monitoring solution isn't even helping us at all. We can go up another level in the condition monitoring strategies and then look at diagnostics. And this is determining what happened. So here we're actually getting to some sort of root cause analysis and getting an understanding of what parts we need to replace, what maintenance needs to be performed. The drawback is that this is going to be typically a little bit more expensive than fault detection, and it's going to require that more data be collected at higher rates. It can often require advanced processing and expert interpretation of that data. The highest level of condition monitoring strategy is what we would call prognostics. And this is determining what will happen in the future. So we're actually making a prediction on what that remaining useful life will be. So maybe we're looking at an expensive piece of machinery and we want to know that if it keeps running the way it's running now, it will break down within the next 7 days. So obviously with this approach, we're going to have the highest reduction in inspection and maintenance cost. However, this is in fact going to be the most expensive condition monitoring solution, typically because it's permanently wired, it's constantly collecting data, the sensors and the equipment is much more expensive, and it may need to be coupled with other data streams as well, like maintenance history, failure history, etc. So let's take a quick look at what some existing condition monitoring solutions look like for these 3 categories. So we do have some instances of permanently installed hardware with wireless solutions where data is collected intermittently. And this can be very advantageous because it's a low-cost condition monitoring solution. We're measuring temperature and vibration, and we can use this to implement that fault detection solution. The disadvantages, of course, are that these types of solutions coming in at the lowest price point might not always be able to enable those higher levels of condition monitoring like diagnostics and prognostics. Another level of condition monitoring solution is what we call intermittent data collection. And this is typically offered as a service where there are maintenance and reliability service providers who offer to show up on site maybe once every month to collect data, or if the maintenance manager believes that a piece of machinery is faulty, maybe someone shows up on site to collect high fidelity, high bandwidth data, and then analyze that offline. So this is oftentimes a very good service, but at the same time, it can be very expensive if we're doing this at regular scheduled intervals, and say the individual responsible for collecting this data shows up on site that day, and maybe that piece of machinery is not running due to its planned downtime. Then you're not able to collect meaningful data and you're not able to analyze it appropriately. So if this is done properly, it can provide a great ROI, but if it's not done properly, it can actually be very costly. And for large plants and large operations where we're looking at deployments of several thousand pieces of machinery or assets to be monitored, oftentimes they're not all going to be able to get this level of attention. A really high level of condition monitoring solution is permanently installed systems with high fidelity instrumentation, data constantly being collected, constantly being analyzed. And this is something that would be used on very, very expensive machinery like turbo machinery that might cost hundreds of thousands or millions of dollars. And any sort of breakdown can be extremely costly to the operation. So it needs to be avoided at all costs. So the obvious advantage is that we're getting that real-time visibility, diagnostics, prognostics, and that real-time prediction of remaining useful life. However, we can typically only give this level of treatment to expensive, extremely critical equipment. So, case study, consider a bottling factory that is a very low margin operation that's running 3 shifts around the clock and is basically requiring the full production capacity in order to generate significant revenue to keep its doors open and keep its lights on. So something like this is going to have lots and lots, hundreds, sometimes thousands of low-cost balance of plant motors. So these motors, while they go in that balance of plant category and are not considered critical from a component cost perspective, they are in fact mission critical. So unexpected failures can result in lost time, lost production, lost money. So in this case, a permanently installed wired solution is far too expensive, and that intermittent monitoring coming out to scope it is too infrequent. So this is a case where something like that lower cost, permanently installed solution that's collecting data once every couple of minutes and sending it wirelessly is giving really good visibility into when faults might be arising and when we might need to give extra attention to certain assets. So to recap how condition monitoring solutions fit into maintenance strategies, across the top, we have our spectrum of maintenance strategies going from run to failure to scheduled maintenance to condition-based or predictive maintenance. And we see that those condition monitoring solutions all feed into that condition-based maintenance program. So using those condition monitoring solutions is what enables the predictive maintenance strategy. Of course, as we go up this spectrum, as I mentioned, we are seeing increasing solution cost. So it's really important to understand how a condition monitoring solution is going to benefit the practice, the maintenance and operation strategies to see what that ROI actually is and how we can actually save money by improving our maintenance strategy. It's also very important to keep in mind that a condition monitoring solution, while it is the most critical component in a condition-based maintenance or predictive maintenance program, it is not the only component. So a lot of times there's this misconception that by implementing condition monitoring, it's completely replacing the maintenance program, when in fact it is supplementing it. And oftentimes, if used properly, is going to be the most critical component in the maintenance strategy, because it is indeed what turns that maintenance strategy from run to failure or scheduled maintenance to condition-based maintenance. But there are other factors that are also used in a maintenance program that we shouldn't overlook. And one of those, which I call sensory heuristics, these are simple indicators like touch, sound, look, that if you've ever been in a factory or you've ever run a factory yourself, and you know an individual who has been running an operation for a very long period of time, they just seem to know when something is going to fail. They know when it looks a certain way or when it sounds a certain way. They can predict that it's going to fail just because they have that level of experience. So that is a little bit more subjective, but it is in fact oftentimes used in maintenance practices. Something that we can also do is take the OEM asset info, so understanding what the model is, what the manufacturer is, how the component is constructed. We could even create physics-based models based on the actual piece of machinery itself. And then there's also domain knowledge, understanding how that piece of machinery operates, understanding how it's mounted. Sometimes certain pieces of equipment are mounted in certain ways where you know that it's going to increase the probability of a shaft being bent or a bearing being worn out quickly. So all of these types of domain knowledge we don't want to neglect. And then there's also the maintenance history as well. So understanding historically how similar assets have performed is something we want to build into our maintenance program. So it's important to keep in mind, while vibration and temperature for condition monitoring should be the most valuable component in a condition-based maintenance program, it still can be used in conjunction with existing maintenance strategies and existing approaches if condition monitoring has not yet been implemented. And of course, the output of this maintenance program is we want to see improved inspections decisions, improved maintenance decisions, and improved operations decisions. So in summary of maintenance strategies, we talked about balance of plant motors, how they make up the largest population, but they typically receive the least amount of attention. And most existing condition monitoring solutions are typically considered premium products just because of their price point. There are lots and lots of new solutions coming to market right now, and over the last probably 5 years, we've seen a lot of breakthroughs in lower cost condition monitoring solutions that we can actually use on the balance of plant motors. So we are starting to see this trend in maintenance and in condition monitoring where we're starting to see technology that's high enough performance at a low enough price point come in so that we can start to blanket an entire factory and at least get some level of visibility into what's going on in every piece of machinery. And we're going to dig into that point a little bit later in one of the other sessions when we talk about vibration-based condition monitoring and we talk about wireless sensors and using the data. But it's important, as I've said, when looking at condition monitoring solutions, considering the ROI and what you're actually putting on a specific piece of machinery, because not all pieces of machinery can realistically get the same type of treatment. So let's dig a little bit more into condition monitoring hardware, and specifically, I'm talking about condition monitoring hardware as it relates to rotating machinery. So this is something that we're going to put on a motor or something that we're going to look at bearings or pumps or compressors, really anything that's rotating or reciprocating. We want to know how we can actually monitor it. So traditionally, some very common components in condition monitoring hardware, the most common is an accelerometer, which is measuring vibration. And we're going to dig into this heavily later and in the second session, but an accelerometer is typically the most critical component in this sort of condition monitoring approach. A temperature sensor will oftentimes supplement that and is very helpful. As you may know, when a motor, for instance, if it's running incorrectly or you're starting to get excessive bearing wear, you could have a temperature spike, and that can help pick up on some of those defects as well. We also have in the hardware itself frequently many microprocessors that are going to handle the sensors. They're going to handle the processing of that data. And in IoT jargon, we call this edge processing. So you've probably heard the term cloud computing because that means that the data is being processed in the cloud somewhere outside of the location that it's being collected. When we talk about an edge device, we're talking about the device that's actually being monitored. So we have the hardware installed on the motor or the component, and we're collecting data on that component and doing some level of processing on it before we transmit it to another location to do further processing. And this isn't for all pieces of hardware, but for wireless, since this is going to be an interesting topic of conversation for us, there's going to be a wireless radio. So taking that edge process data and communicating it over radio frequency, oftentimes Bluetooth. It will oftentimes have a battery and then sometimes some additional memory to log data as necessary for various use cases. So how are the sensors used? When we're looking at the accelerometer, which we're going to do a deep dive in later, the data is collected in many different ways and it can be processed in many different ways. But basically what we're doing is we're looking at machine motion at various frequencies and collecting that vibration data and then processing it to try to relate that vibration behavior to system health. So when we process the data on the device itself, we're looking at calculating metrics that are related to machine health. And this actually helps us quite a bit by doing some processing on the device. We can reduce the amount of data that actually needs to be sent or transmitted wirelessly if we're doing it wirelessly, and that can save on battery life. However, just using edge process data could potentially limit our variety of use cases and our ability to perform maybe diagnostics or prognostics. So oftentimes we will also have the ability to collect raw or unprocessed data that we can take off the device and then go elsewhere and do advanced processing on it. So maybe we have a software package or a different UI that we're using or feeding it into a different system that's doing some heavy lifting on this data. And we're oftentimes looking at much, much larger data sets because this is high bandwidth data. But of course, as I mentioned before, this usually requires some sort of expertise to do the analytics and to actually interpret the data. For the temperature sensor, it's oftentimes a little bit simpler. So we can measure the temperature of the asset under consideration, and we can also measure the temperature of the environment that it is installed in. So we could place a simple temperature threshold level and say, when it rises above, for instance, 200 degrees Fahrenheit, we think that something is seriously wrong, so we set a threshold there. We can also look at how the device or the asset is trending with the actual temperature in the environment that it's installed. So oftentimes we'll be looking at temperature on the asset itself and then also in the operating environment. So back to our discussion on the range of condition monitoring solutions. Oftentimes we categorize it like this for simplicity, where we say, okay, for increasing cost, if I spend a little bit of money, I know that something happened, and I spend a little bit more, I want to know what happened, and then I spend a lot of money, I can start predicting when something will happen. However, this compartmentalization isn't oftentimes this clean in practice, and we're going to usually have overlap. So when we're looking at lower cost fault detection solutions, the something happened could just be simply a change in vibration state, but it might not necessarily have the high level of accuracy that we want it to have. So keep in mind that as we increase the cost of our condition monitoring solution, we're increasing the capabilities, but that level of accuracy and having that high level of confidence where we're not getting a lot of false positives and false negatives sometimes is very difficult at the lower end of the spectrum. So that's just something to keep in mind when considering different condition monitoring solutions. And like I said before, it's very important to consider what the ROI is across that entire spectrum. Like I said, there is an inherent trade-off between false negative rate, which is saying something's healthy when it's faulty, and a false positive rate, which is saying something is faulty when it's healthy. So if we had a high false negative rate, it's basically saying that something is always healthy and we're never alerting, we're going to miss everything. If we have a system that's tuned in correctly, we can get a high level of alerts, but once again, that could increase our inspections costs, and that's not going to be helpful to us. So we oftentimes have to look at what is the balance when setting different threshold levels on vibration, or even using more advanced machine learning approaches like I will be talking about in a later session. We have to find what that balance is to understand how this is actually going to help us in our practice. So I'm going to dig more into these sensor specifications later when we talk about vibration-based condition monitoring, but this is just a snapshot of what a spec sheet would look like. And if you've never seen this before, I wouldn't expect this to make much of any sense to you. But what I want to do is kind of simplify this and distill this and say, okay, what is important when selecting a condition monitoring solution? So oftentimes what we're concerned with in condition monitoring is the frequency response of the device. And this is basically saying, how does the accelerometer respond when we excite it at different frequencies? And because based on that, we're going to be able to detect different types of faults. So this metric right here, or this performance characteristic, the frequency response curve, is very important. And I'll talk a little bit about this more in session 2 when we dig into the physics of vibration. But it's important to keep in mind that not all accelerometers perform the same way, and they do have various performance curves. So when it comes to the world of vibration-based condition monitoring, the most important thing that you want to look at with selecting a sensor is what we would call its bandwidth. And this is simply the range of frequencies that it's able to detect. And this is something that we all experience in our daily lives. So when we're talking about vibration, we're talking about physical, mechanical movement. And we experience this daily when we listen to things, because sound itself is a mechanical vibration. It is just simply air vibrating, being excited by some source. The air vibrates, it makes its way to our eardrum, and then we're able to detect various sounds, various pitches, various frequencies. So consider this sound analogy. Say that you are at a soccer match and a referee blows a whistle. So when the referee blows the whistle, air goes through the whistle and it causes a vibration of the air. And that air vibrates and it makes its way to your ear, where it actually physically causes your eardrum to vibrate. And when your eardrum vibrates, it actually causes electrical pulses that make their way to your brain, and your brain, having been exposed to these electrical pulses over time, knows, it's been trained and it's learned that this is the sound of a whistle. However, if you were standing right next to someone and they pulled out a dog whistle, which we know it's meant to operate in a way so that a dog can hear it and a human cannot, the dog whistle operates just like the referee whistle in the sense that it vibrates the air. But for a human, that vibration is going to make its way to the human ear. It will cause really small electrical pulses on the eardrum, so small, in fact, due to the fact that it's such a high frequency that the human brain is not even going to recognize it. And your subjective experience is that nothing is happening. You wouldn't even know that the whistle's being blown. However, of course, if a dog is standing nearby, a dog having eardrums that support a much higher bandwidth, in other words, they are able to detect much higher frequency levels. When that same vibration hits the dog's ear, it's going to create electrical pulses that its brain is going to interpret as a whistle, and it can hear it. So the same exact thing is true with vibration-based condition monitoring. We will have a motor or a rotating piece of rotating machinery that is vibrating. It causes mechanical, physical vibration. And in this case now, a sensor mounted to it is what picks up that mechanical vibration and converts it into an electrical signal. And then we can do processing on it with edge processing or cloud processing using AI, machine learning, et cetera, and then interpret that with advanced algorithms and data analytics techniques and determine whether or not there's an actual fault in a piece of machinery. So for your reference, if you're looking at an accelerometer spec sheet, like I said, the most important thing is bandwidth. And if you look at the specifications for a piece of hardware, all of the specifications and their performance are really built around supporting higher bandwidth pieces of instrumentation. So if you're able to detect higher frequencies mechanically, you also want to collect data at a higher rate. So this would be what we call sampling rate. So if we have high bandwidth accelerometers, we also want to see high sampling rates to support them. And then of course, if we have a higher bandwidth, that means we're detecting more frequency content, which basically means there's more signal, overall signal that we're seeing, and we have to actually increase the dynamic range as well. So when we start talking about sensor specifications like an accelerometer that measures 10 Gs or 32 Gs or 64 Gs, that's what we're talking about with dynamic range. And increased dynamic range means that we also now have to increase the resolution of the signal, because we're now looking at a higher range of measurement values. So we want to increase that resolution so we can capture them all and still capture them all accurately. And then also, when installing instrumentation, even the way that you mount it matters, because it's going to affect the mechanical structure. It's going to affect the way that something vibrates. So if we can bolt something on, that's typically the most secure way, but epoxy mount or magnet mount or something like that is oftentimes very useful as well for preserving that mechanical structure and capturing all of that vibration content. So we can expect that we're going to see different rotating machine faults at various frequencies. And this is by no means comprehensive or applying to every scenario, but in general, normally we're going to see certain faults manifest at different frequency levels. So something like looseness or improper mounting, that's usually a lower frequency event. And this is the kind of thing that you can typically see with your eye, or you can hear it. It makes a lot of noise. As you move up the spectrum, something like a motor being installed at the wrong angle, so misalignment, or there being some imbalance if there's a bent shaft, this is going to happen more in the middle range. And then at mid-range frequencies, we can actually start to pick up on what we call late-stage bearing defects. So this is a bearing right at the end of its life. If we want to pick up on early stage bearing defects, though, we are normally going to have to go much higher in the frequency spectrum. And then also, if we're looking at monitoring a gearbox and we want to find something small like a crack in a gear tooth, we're typically going to have very high bandwidth instrumentation that's collecting data at very high rates in order to detect that. So as I said before, an accelerometer, it measures acceleration, but acceleration as a vibration metric is not always the most useful for detecting some of these faults. So sometimes we're going to take that acceleration signal and we're going to convert it into other signals, such as displacement or velocity, in order to detect different types of defects. So displacement, when we're talking about displacement, we're just looking at a distance change. So think of real world application, if you're driving your vehicle and you go from block, 20th Street to 21st Street, your vehicle has been displaced by one block because it's moved one block. So that's what we're talking about. This is in units of distance, so something like inches or millimeters or feet. Velocity is typically better for picking up kind of these mid-range defects, and we can think of velocity basically as the time rate of change of displacement. So if you move that one block over a certain amount of time, you might be driving at 20 miles per hour. That's going to be your speed being the magnitude of velocity. So this is going to be in something like inches per second or millimeters per second, or with a vehicle, miles per hour. And then acceleration, of course, is typically better at picking up the higher frequency defects. And we can measure this, as I said before, in Gs, where 1 G is equal to 9.81 meters per second squared, or 32.2 feet per second squared. But this type of processing oftentimes gets done on the device, where we take that raw accelerometer signal that's measuring acceleration and we perform calculations on it to turn it into a velocity signal or a displacement signal. And that's going to help us to detect different types of defects that occur at different parts of the spectrum. So to put this all together, high-level look at what a maintenance workflow would look like with a condition monitoring solution enabled. So we would install our condition monitoring hardware on an asset, and it's going to monitor and collect that vibration data. That data is going to be processed maybe on the device or processed elsewhere off the device, like maybe in the cloud. And then if we detect a change or believe that there's a fault, we're going to issue an alert and send a notification, maybe via email or text message, to a maintenance manager or whoever is in charge of operations. And then oftentimes we can do a deeper dive at this point. So maybe we have several assets that have sent alerts. So maybe we have a floor with 100 assets and we have alerts on 3 of them. So then we would go and collect higher fidelity data, specifically target those 3 assets, collect higher fidelity data, go back and analyze it and do more advanced processing, like something like a Fourier transform, which I will touch on a little bit more in our second session. But we can do more advanced analytics on this and really start to get into that diagnostics and maybe potentially prognostics. And then, of course, based on that, maintenance can then be performed based on the known state of a machine. So this concludes session 1. And like I said, I'm going to dive into the fundamentals of vibration-based condition monitoring more in session 2. And at that point, we'll be talking about more of the physics of vibration and looking a little bit more at the technicals of the data.
Well, thanks, Brad, for what was really a very comprehensive presentation, and I'm looking forward to seeing the other 2 parts. We look forward to seeing you in the live Q&A session immediately following. Be sure and have your questions ready. Thanks for joining us, and we hope the information provided will suit your purposes. Questions will be answered in a live Q&A on April 1st at 10:45 Central, 11:45 Eastern. Participate in the live Q&A with your Zoom invite details. These details can also be found in the Additional Resources tab on the left-hand side of the screen.